Good afternoon. We are from Group 6, and today we're going to present our systems modeling final project. Next. Here are our group members. Next. Bangladesh is one of the most disaster-prone countries in the world due to its geographic location, topography, and high population density. It frequently experiences natural disasters such as earthquakes, floods, and especially tropical cyclones, which severely affect southern regions. In this project, our goal is to design, simulate, and compare various logistics strategies for delivering 80,000 tons of disaster relief goods to the affected regions of southern Bangladesh within a 40-day period, serving approximately 2 million people. However, there are several general constraints that we must consider in the planning and simulation process. These include damaged infrastructure, limited accessibility to remote or flooded areas, budget constraints, and overall logistical limitations due to the scale of the operation. The map highlights the cyclone-affected areas and underscores the urgent need for an effective and adaptive logistics plan. Next. Now let's talk about the demand, supply sources, and key constraints. Around 2 million people in southern Bangladesh need shelter, food, medicine, and fuel. The total demand is 80,000 tons over 40 days, equivalent to 2,000 tons per day or 1 kilogram per person per day. In the first 5 days, 10,000 tons will be distributed from government stockpiles in Dhaka, Chittagong, Khulna, and Pabna. From day 6 onwards, 70,000 tons will arrive internationally, mainly from Singapore via Dhaka Airport and Chittagong Port. There are major infrastructure and transport constraints. Roads are impassable for the first 2 days. Some bridges cause delays, and port access is limited to Dhaka and Chittagong. Early transport relies on helicopters, which are costly and limited in capacity. Small trucks can operate from day 3 and larger ones from day 15. Planes and ships offer longer range, but with high costs and delay. The key point is that relief efforts must adapt to shifting access and transport options as infrastructure gradually recovers. Next.
Okay, so this is our model simulation video. Okay, so for our model conceptualization, firstly for the transport modes and availability, by air helicopters, day 1 onwards, and for the ground, 3-ton trucks is from day 3 to 14 only. Then for ground, 6-ton trucks is for day 15 onwards, and for international ship and plane is from day 6 onwards. And our modeling approach is that by using linear programming to optimize the logistics plan, and by focusing on minimizing costs while maximizing delivery effectiveness, and where the LP accounts for daily demand, cost of each mode, availability over time, and impassable infrastructure.
Okay, here is our model constructions. So for the key properties, there are source, server, and sinks. And the source is divided into two types, such as vehicle types and goods from different location. And server consists of loading and unloading of goods from or to different location. And for the sink, it is receive the end products after different paths. And for the combiner, so combiner function to combine the path from different nodes. And for the separator, so separator 1 or Boeing and separator 2 and ship is to separate the goods going to sink or continue, and separator 3 to decide sink to come or vehicle. Next. So here is our model construction.
And to verify our model, first we check the flow works, which is the entities moving smoothly from the source throughout the servers until the sink. Second is the connections validity, which means that all blocks are properly linked with no breaks. Routing logic, meaning the decisions and branches are connected correctly. Fourth is there are no stuck items, meaning no loops or dead ends. Fifth is the resources and or queues are present, meaning that buffers and processes are working. And finally, the final output, meaning that items exit correctly at the sink. And to validate our model, first we check the delivery achievement. The model successfully transported 78,282 tons of the targeted 80,000 tons, meaning that we reach over 97% fulfillment. Next is the deadline adherence. The model delivered the plan within the 40-day period. The cost performance, meaning that the total cost of logistic was $25 million, which means we demonstrate the cost effectiveness compared to the total value of goods. And finally, the overall assessment, meaning that the model produces credible and practical outcomes and satisfies the logistical requirements outlined in the disaster response scenario. So from all this, we can take the key takeaways are that the model is both valid and reliable for evaluating relief distribution strategies, effectively balancing cost and timeliness while supporting scenario experimentation for decision making under uncertainty.
Okay, for the model usage, we implement the workflow logic. The first one, visualize the entire workflow and material flow. Next, identify bottlenecks in the process. And then we improve decision-making through data-driven simulation. And then optimize resource usage such as machines and transporters. And then we estimate performance metrics like throughput, delays, and cycle times. The data approach that we're collecting is average wait time in queues, machine utilization, total output, item processing time, like cycle time, and then number of times rework or scrap. Next.
Okay, so for the next one, so we can conclude uh, for the summary of our key findings and the best logistics schedule. We built a logistics model that identifies cost-effective strategies while staying within budget. And then the model proves that delivering 80,000 tons of relief in 40 days is possible, even with damaged infrastructure. And next one is it offers a reliable foundation for real-world disaster planning. For our solution, now for the best schedule, day 1 until 2 helicopters from local stockpiles for inaccessible areas, no extra cost. And then day 3 until 5, small trucks begin operating where roads are partially open, also no cost. And then day 6 until 11, emergency air shipments distributed by small trucks cost 34.72 million. And then day 11 to 39, boats bring bulk goods distributed by small plus big trucks cost 10 million. And then for the day 40, final top-up by plane already included in earlier cost. And for the impact, we use boats for inbound shipping and big truck regional delivery. So overall, this plan balances speed and cost, making it ideal for large-scale disaster response. Okay, so here's our appendix. Next. Okay, that's all from us. Thank you for listening to our